We're going to take a look at a couple of special cases with systems of equations. So here I've got a system of equations, y equals 2x plus 1 and 2y equals 4x minus 8. And I want to solve that using one of the methods that we've been learning. Since this one is already set up with a y equals, it makes the most sense to use substitution, because we can right away take the expression 2x minus 1 and substitute that in for y in the other equation. So that's what we're going to do. I'm going to rewrite that second equation, replacing the y with the expression 2x plus 1. Everything else stays the same. So we'll go ahead and distribute that 2, and that will give us on the left side of the equal sign 4x plus 2 is equal to 4x minus 8. So something might already look like different from the other, from other systems that we've solved. But we'll go ahead and solve anyway. I'm going to get that x term on the left side, so I'm going to subtract that 4x from the right and then balance it out, subtract it from the left. What that gives me is that 4x cancels out and I have 2 on the left. That 4x cancels out. I have negative 8 on the right. So this is something that we haven't really seen yet. We solved this system and the x term, or the variable term, got canceled out on both sides, and we're left with this statement that says that 2 equals negative 8, and that is not true at all. When you get a statement like that where the variable terms cancel out completely and you just have a statement about numbers, if that statement is false, you have no solution. There is no value of x, no value of y that you could substitute in to this system of equations that'll make it true at the same time for both equations. I want to take a look graphically at what's going on here. So our first equation in the system was y equals 2x plus 1. So we had a y-intercept of 1 and a slope of 2. So when you increase x by 1, y increases by 2. So write 1 up 2, write 1 up 2. And we have all of these points. And we have this line for y equals 2x plus 1. The second equation was 2y equals 4x minus 8. And that's not in slope-intercept form. We'll have to divide that all by 2 to get y equals 2x minus 4. That one has a y-intercept of negative 4 and a slope that's also 2. So when we increase x by 1, y goes up by 2. So write 1 up 2, write 1 up 2. And we plot all these points. Now normally when we solve a system graphically, what we're interested in is where these two lines intersect. But since the slopes are the same, they're never going to intersect. We have two parallel lines that have no intersection point at all. So when you have graphically two lines that never intersect, that should indicate that you have no solution. This system of equation has no solution. There are no solutions that this line shares with this line, or that this equation shares with that equation. So that's special case number 1. If you have parallel lines, or if your variable terms drop out and you have a false statement like 2 equals negative 8, you have no solution. Take a look at one more here. We have 2x plus y is equal to 10, and 4x plus 2y is equal to 20. So in this case, it's set up in a way where elimination will probably be the best way to solve this. I'm looking for any place I could get opposite coefficients, and I'm looking at this thinking I can make that 2x a negative 4x, which would allow me to cancel. So I'm going to multiply this first equation by negative 2, and that will allow me to get opposite coefficients. So negative 2 times 2x is negative 4x minus 2y equals negative 20. And I don't need to change that second one at all, so I'll just bring that over as 4x plus 2y is equal to 20. Now that I have opposite coefficients, I'm going to add down those columns. So I get 0x plus 0y is equal to 0. The x term is gone, the y term is gone. On the left side, I have nothing. I just have a big 0 on the left. On the right, I also have a 0. So the variable terms canceled out again, but this time we got a statement that is true. 0 is equal to 0, which indicates we have another special case, infinite solutions. if both of your variable terms cancel out and you're left with a statement about two numbers that is true, that's always true, like 0 equals 0, you have infinite solutions. Let's take a look at this one graphically also, and we'll see what's going on here. So our first equation was 2x plus y equals 10. Now that's not in slope-intercept form, so we'll subtract 2x from each side. And y is equal to negative 2x plus 10. So we have a y-intercept of 10. Slope is negative 2, so when you increase x by 1, y decreases by 2. So write 1 down 2, write 1 down 2, and we have all of these points for our line. So there's the line y equals negative 2x plus 10. The second equation was 4x plus 2y equals 20. So we'll subtract 4x from each side. That'll give us 2y is equal to negative 4x plus 20, divided all by 2, and y is equal to negative 2x plus 10. So our second equation has a y-intercept of 10. So we'll go ahead and start this one up on the y-axis at 10. Well, that's where we have a point. Slope is negative 2, so when we increase x by 1, decrease y by 2. So write 1 down 2, write 1 down 2. And we are replotting all these same points that we did before. Essentially, both of these equations result in the same line. When we solve a system graphically, we're looking at where do these two lines intersect? Well, these two lines intersect absolutely everywhere. There is an infinite number of solutions. This system has an infinite number of solutions because those lines intersect everywhere. When you solve a system of equations, there are three things that could occur. So I want to think about those in a visual way. The first thing we learned is about two lines intersecting in one place. So if you have two equations that intersect, or when you graph them, intersect in one spot, that is one solution, the intersection point. Then we saw a special case where we had two parallel lines, and parallel lines never cross, so they have no solution. The third case, which we just saw, is when we have equations that graph as the exact same line. So if they graph right on top of one another, they intersect everywhere, and what we have are infinite solutions.